From the earliest moments of human consciousness, time has been an enigma, a river flowing forward relentlessly, dragging everything in its current. We mark it by the rising and setting of the sun, by seasons and years, by clocks and calendars. But what if that steady stream is more illusion than reality? What if time, as we perceive it, is just a construct layered over a deeper, stranger dimension? The desire to escape the confines of the present, to revisit moments long past, or to glimpse futures yet unwritten, has fueled myths, stories, and dreams across cultures for centuries. Yet, despite the many portrayals in fiction and pop culture, true time travel does not align with the fantastical images of blinking machines or wormholes that swallow you whole. Instead, it requires us to rethink the very fabric of the universe and our place within it. Physics, the language through which we understand the universe, tells a story far more subtle and complex than the simple ticking of a clock. Albert Einstein's theories of relativity revolutionized this understanding, revealing that time is not an absolute uniform flow, but a flexible dimension intertwined with space itself. Space and time, combined into the four-dimensional continuum of spacetime, bend and stretch under the influence of mass and energy. This revelation cracked open the possibility that under extreme conditions, near black holes or at speeds approaching the speed of light, time could behave in ways that defy everyday intuition. Clocks on spacecraft orbiting Earth tick just a fraction slower than those on the planet's surface. Astronauts returning from space are infinitesimally younger than their Earthbound twins, a real-life glimpse of what was once pure speculation. This phenomenon, known as time dilation, is the closest confirmed experience of time travel science offers, a journey forward in time. However, it is not the thrilling leap into a distant future portrayed in stories, but a subtle distortion measurable only by the most precise instruments. Yet it lays the foundation for the argument that time travel is possible, though not by hopping into a machine that rewinds the clock or catapults you into the past. The past in this context is not a playground to revisit. It is a fixed sequence of events that cannot be undone or re-experienced as a traveler might hope. But if the past is off limits and time dilation only allows a one-way ticket forward, what does this mean for our dreams of time travel? It means the key lies not in traveling through a linear timeline, but in understanding that time itself might not be a simple line at all. Modern physics suggests time could be more like a landscape, with many paths and folds, a block universe where past, present, and future coexist simultaneously. If so, the common notion of moving backward or forward like pages in a book is misleading. Instead, traveling through time might mean shifting perspective within this block, revealing how moments are interconnected in a far more intricate web than a straight arrow could capture. As these ideas take hold, new theories emerge that challenge the conventional narrative. Quantum mechanics, the physics of the very small, introduces uncertainty and probability into the heart of reality, blurring the lines between past and future. Some interpretations propose the existence of parallel timelines or multiple universes, each representing different outcomes of events. These suggest that what we perceive as a single history might be just one thread in a vast tapestry of possibilities. The tantalizing concept of many worlds opens the door to versions of time travel that don't alter a single timeline, but allow movement between parallel realities. In this vision, time travel is less about changing your own past and more about navigating between the branches of an ever-expanding multiverse. Yet these ideas remain speculative, largely beyond the reach of current technology or empirical testing. The practical challenge of traversing these landscapes, whether through space-time manipulation or quantum jumps, is immense. Even the most optimistic theories involve conditions or energies far beyond what humanity can currently harness. Still, the theoretical possibility forces us to question the rigid barriers we assume time imposes. It pushes us to see time not as a strict tyrant, but as a dimension that can be bent, twisted, and perhaps in ways subtle or profound, traversed. As this understanding settles, it becomes clear that time travel is possible, but not in the explosive, science fiction manner most imagine. It is a phenomenon rooted deeply in the universe's fundamental laws, accessible not through whimsical devices, but through the mind-bending realities of relativity and quantum theory. The future traveler is not a daring adventurer hopping into a machine, but a physicist deciphering the elegant dance of space-time, or a cosmic observer witnessing the fluid nature of time itself. To truly grasp how time travel could exist beyond fiction, one must venture into the labyrinth of theoretical physics where the known laws of nature push their boundaries and reveal hidden doors. The journey begins with the concept of space-time curvature, a cornerstone of Einstein's general relativity. According to this theory, massive objects like stars and black holes don't just sit in space, they warp the fabric of space-time itself. This warping isn't a static indentation, but a dynamic curvature that affects how time flows. Near a black hole's event horizon, the point of no return, time stretches to extremes. For an observer watching from afar, a clock near the horizon ticks slower and slower, appearing to almost freeze at the edge. For the traveler close to the black hole, however, time passes normally. This divergence in time's pace is not fantasy. It's a consequence of gravity's profound influence. This leads to the intriguing possibility that if one could survive such extreme environments, they could experience time at a drastically different rate than someone far away, effectively traveling into the future. Yet the journey to a black hole's edge is perilous, and the crushing gravitational forces are beyond any current technology's capacity to shield against. Still, this theoretical pathway illuminates the way nature already permits a kind of time travel, a one-way ticket into tomorrow. Another tantalizing notion arises from the concept of wormholes, hypothetical tunnels connecting distant points in spacetime. Imagine spacetime as a folded sheet of paper. By folding it, two points that seemed far apart could be brought into direct contact. Wormholes could, in theory, create shortcuts through space and time. If stable wormholes exist and could be traversed, they might enable travel between different times or locations almost instantaneously. This idea, popularized in science fiction, is grounded in real physics equations, but it comes with monumental caveats. Wormholes, if they do exist, would require exotic matter with negative energy to keep them open, a substance that has not been observed and may not be physically possible. Even if such exotic matter could be harnessed, manipulating wormholes to travel through time would raise paradoxes and complications that challenge our understanding of causality, the cause and effect sequence that governs reality. The famous grandfather paradox, where a time traveler could potentially prevent their own existence by altering the past, highlights these logical tangles. Some physicists speculate that nature protects consistency through mechanisms that prevent paradoxes, or that every change spawns a new parallel timeline, preserving the original history intact. Quantum mechanics further complicates the picture by introducing fundamental uncertainties and probabilistic outcomes at the smallest scales. The intersection of quantum theory and general relativity remains one of the greatest mysteries of modern physics, hinting that the ultimate nature of time might differ drastically from our classical notions. Some speculative frameworks, like the theory of quantum gravity, attempt to unify these forces and suggest that spacetime itself is quantized, made up of discrete chunks rather than a smooth continuum. This could open doors to understanding how time might be manipulated on a fundamental level, though practical application remains far off. Another intriguing approach to time travel comes from the concept of closed time-like curves, paths through space-time that loop back on themselves. In theory, if such curves exist, an object following one could return to its own past. Solutions to Einstein's equations, such as those proposed by physicist Kurt Gödel, suggest these curves are possible under certain exotic conditions. But again, the physical reality of such environments is questionable. The existence of closed time-like curves also invites philosophical questions about free will and determinism, forcing us to confront whether the past is fixed or fluid, and whether altering events is possible or an illusion. These theoretical explorations illustrate that time travel is less about instant leaps and more about understanding and navigating the complex geometry of the universe. It's a subtle dance of gravitational fields, quantum uncertainties, and space-time topology. The vision of a glowing capsule hurtling through time is a poetic oversimplification. Instead, time travel, if it can be called that, is a phenomenon arising naturally from the physics governing our universe, waiting to be understood rather than built. In practical terms, humans already engage with time travel daily, albeit in a minimal sense. Satellites in orbit must account for relativistic time dilation to synchronize GPS signals accurately. Astronauts age slightly slower than their Earthbound counterparts. Particle accelerators observe particles that live longer when moving at near light speeds. These small but real manifestations of time's flexibility confirm that time is not absolute but relative, malleable under certain conditions. The frontier of time travel research now intersects with the quest to unlock quantum computing and the mysteries of black holes. Some theorists propose that the interior of black holes, or the entanglement of quantum particles, could serve as conduits for information transfer across time or space. These ideas remain speculative but are being actively investigated through mathematical models and experimental physics, pushing the boundary between science and science fiction. Ultimately, the path to understanding time travel is not about conquering time itself, but about expanding our comprehension of reality's deepest layers. It invites us to embrace a universe more complex and wondrous than our everyday experiences suggest, where time's flow is a thread woven into the grand tapestry of existence, flexible yet bound by profound laws. Time travel is less a technological challenge and more a conceptual revolution, a journey into the unknown terrain of space-time's hidden geometry. As the threads of physics weave together a vision of time far removed from everyday intuition, it becomes clear that time travel, rather than being a destination, is a process woven into the very fabric of existence. The future of time travel research is less about building machines that break the timeline and more about unlocking the subtle ways the universe already allows moments to stretch, fold, and interact. The challenge for humanity is to step beyond the simple passage of seconds and embrace time as a dimension we can explore in new, profound ways. Imagine a future where the boundaries between past, present, and future are not rigid walls but permeable membranes, where understanding and manipulating the geometry of spacetime could allow us to peer into what was or what might be. This vision does not promise casual trips to ancient civilizations or visits to tomorrow's cities. Instead, it offers a deeper engagement with the flow of time, where advanced technologies harness relativistic effects or quantum properties to extend human perception and experience. One avenue of this emerging future lies in the integration of quantum information, science, and gravity. If the secrets of quantum entanglement and black hole thermodynamics can be fully understood, they might reveal ways to encode and retrieve information across time. Instead of physical travel, this could mean communication or observation beyond conventional temporal limits, receiving messages from the future or extracting records from the past, encoded in the quantum fabric itself. Such breakthroughs would transform time travel from a physical journey into a form of transcendent connection, allowing humanity to engage with time on a fundamentally new level. Parallel to this, advances in space travel technology might one day make time dilation more than a curiosity. Human voyages at speeds approaching light or near massive celestial bodies could create extended lifespans and journeys into the future, not by bending time dramatically, but by moving within its natural contours. The time traveler of the future might be an astronaut or explorer who, by navigating the cosmos, steps naturally into tomorrow, returning with insights shaped not just by distance, but by time itself. The philosophical implications of such capabilities are staggering. If time is a landscape of possibilities rather than a linear chain, then human choice and consciousness become intertwined with the universe's structure in unprecedented ways. The notion of fate and free will may blur as every decision branches into myriad timelines, and the act of observing or measuring affects outcomes. In this light, time travel is not about escaping consequences, but about participating consciously in the unfolding of reality. Moreover, understanding time's true nature reshapes how we think about memory, history, and existence. Our memories are fragments of past moments encoded within the present brain, but if the past exists simultaneously in the block universe, those moments are accessible in principle. though whether they can be experienced directly remains an open question. This challenges the limits of human experience, suggesting that the mind itself may hold keys to navigating time in ways yet undiscovered. Yet for all the wonder and possibility, the practical challenges remain daunting. The energies required, the exotic conditions needed, and the profound paradoxes to navigate ensure that time travel, real time travel, is not a casual endeavor, but a frontier for the most advanced physics and technology. It is a quest that demands patience, ingenuity, and humility before the universe's vastness. In the meantime, the stories of time travel continue to inspire. They remind us that our understanding of time is still young, and that the universe holds mysteries waiting for brave minds to explore. Time travel is not just a scientific puzzle, but a metaphor for humanity's relentless curiosity and desire to transcend the limits of experience. In embracing time travel's true nature, we embrace a universe more intricate and beautiful than simple clockwork. We acknowledge that time is a dimension as rich and varied as space, shaped by gravity, quantum chance, and perhaps even consciousness. The traveler through time is not merely a passenger, but a participant in the unfolding cosmos, journeying not through corridors or machines, but through the very essence of reality. This is time travel as it is possible, a profound shift in understanding, a journey not of leaps and bounds, but of insight and wonder. It invites us all to look beyond the illusion of a ticking clock and step into a timeless dance with the universe itself.